Ça, comment le mettre en place? Comment le mettre en place? Comme ça, je pense. Non. 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 Peut-être que ça.
Ah, j'ai pas.
Ah, pour retirer ça?
Il se retire tout seul.
Non, non, justement. Peut-être en plus.
Non plus, ouais.
Peut-être non plus, il y a.
Ouais, c'est ça.
Comment ce nombre de réunions?
Ouais.
Tu sais
En
comment
dessous, en dessous, en dessous, en dessous, voilà.
Ok, c'est bon. Et ça marche?
Oui, ça
Oui, 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 on voit.
So, hello everybody. I'm happy, especially these FreeFem days, because I start a permanent job finally after 12 years of working with FreeFem. I'm as an engineer at CNRS in Laboratoire LMRS at Rouen. And I will present you some numerical simulations that I done with FreeFem++. So I will not enter in the detail of all what I will explain. Frederick was asking how to build the intersection with the meshes in 2D. So I did it now in 3D with 3D meshes. And for the code, I will show you at the end. So the first thing I want to speak about is a toolbox which has a free and published for the parallel finite element code for the simulation of 2D and 3D solid liquid phase change system. We have here the Navier-Stokes equation and here for the heat equation. And the simulation of this equation. For the left, we have a fusion of a paraffin, which is solid at the beginning. We heat from below, and we use here mesh adaptation, and we have the convection cells that goes up. Here we use for the water solidification. We get the temperature from -10 and from 0 to -10, and we have the ice that start to created inside the water. Another application that I've done for the numerical simulation of the blood inside an arteria. We have here for the lumen, we have the Navier-Stokes equation. For the cholesterol, we have a advection diffusion equation. And in the intima, we have a Darcy equation, and for the cholesterol. And the simulation of this, we have the Navier-Stokes fluid, which goes from left to right. And here the Stokes is, the cholesterol is stored here. And FreeFem cannot generate the mesh at the end, and the patient is dead already. Another application is for Boussinesq for water wave equation. So here we have the Boussinesq BVM equation. With a water wave that goes across a hardcore. For Frederick Asht, I took a code from him how to build a mesh from an image. So here I'm interested to this zone to generate the mesh from here. And here's this, there is a website to take the bathymetry also of a special zone in the Earth. So you can use this website to obtain the bathymetry. So here I will show you a simulation on a mesh generated by FreeFem for the tsunami here near Cyprus. And the code and okay, so before the code, here is another slide for how the when we have an earthquake under the ground, how the slice of the topography will move. So here we have some parameters and equation, and here there is a function here zeta that using this we can generate what's happening in the Java island near the epicenter was here. In this paper, you have the toolbox for how to generate a mesh from an image, how to generate the mesh from a bathymetry. So here, I generate the mesh from the bathymetry, and I simulate the tsunami wave generated for near Java Island in 2016. Another simulation, we can use finite difference with FreeFem if you are on structured grid and you use P1 finite element. So here, for example, for shallow water equation, and another simulation for the water to fill this part. We can use also FreeFem to solve shallow water equation with XNav, coupling with XNav. So here for the dam break, we have so even with the shock, there are taken into account. Another application is for with finite volume for the dam break of Malpase. So here we have also a domain adaptivity domain adaptivity mesh, and it works also with the FreeVol. We can mix finite element and finite volume equation. For example, here we have the hyperbolic part that we wanted to use to solve in finite volume, and the other part in finite element. So in order to do this, we generate two mesh. The first mesh is square here, and from the barycenter of this mesh, we build another mesh, use it for the P1 finite element. And since the solution in P1 are on the vertex and on the P0 are on the barycenter, so we can interpolate and bring solution from P0 to P1 or P1 to P0 without losing anything. And as application, so here is only with, for the finite volume, it's only BD equal to 0, and here another solution for BD difference than 0. Another application also done with FreeFem is on this paper. So here the first equation is as a Schrodinger nonlinear equation. It's for Bogoliubov, for Bose-Einstein condensate, and the solution here, for example, is a dark soliton, and we can do an eigenvalue problem for the computation of the stability of the solution obtained as for Bogoliubov region stability, and here you have the value, the real eigenvalue and imaginary part. Things can be more complicated if you use two components, but with FreeFem it's easy to build the code from starting from one component to two components. So here a result for two components with the ring here coupled with Thomas Fermi. So I'll not enter in the detail of the physical problem, but I'm showing you just what we can do. So this is also a toolbox which will be also free and distributed for the 3D case in parallel. So here we have a solution with a huge number of unknowns of one vortex line and two straight lines. And at the other side, the real eigenvalue and image eigenvalue. Another application also, if you add the rotation for the GP equation, we have this kind of good solution for rotation of the vortex. And we are interested to detect or identify the vortex in quantum fluid for all the other simulations that I've done or that was done with FreeFem. So here we have wanted to detect all the vortex in the 2D and all the vortex line in 3D. So also there is a toolbox with FreeFem that we can do this, and it's already published. We can get more complicated in quantum turbulence, and we can get a line of all the vortex obtained there. We can also compute the Kelvin wave spectrum and do some statistics on each line if you want. There is special things for Olivier and Frederic. So some tricks in FreeFem that I learned from 1 year till now in my last postdoc. I have a mesh here, so I can use include mesh surface.edp. I can generate the sphere using the sphere 20. I can remove internal edge using the change, and I can change all the region to one region. And what I'm interested is, I defined a solution on this sphere, and I wanted to get the isoline obtain one isoline on the sphere of this function. If I use MMGS like this, I put here LS equal to 1. It is the values of isosurface that I wanted. So here I get two isosurface, two isoline, and I want to mesh it or count it or play with it. So using this, the mesh obtained will give 3 regions. I can use the trunk for the special regions that I want, and I will remove it. I will rename it like this for 0. So here I have 2 holes in my sphere. I can use extract to build only the line of all the labels of THS, which here are 2 lines. I can use also a new thing, yes, to separate the component with connected components that are in the module mesh tools. So here we obtain that we have 2 meshes that are separated. The NBC is 2, and we can build the mesh now with build mesh S. Using build mesh S, we can trunk the line of each value. So each line here is trunked. Using build mesh S lab, it gives a surface, minimal surface using Laplacian on over the board. So this is a new done by Frederic. And we can also add all the surface that we have. And now, since we have the vertex are common between all surfaces, it can be added. And finally, we can generate a mesh using tangent of this domain. So this is what I played from 1 year ago. And the other thing that I played is I was a postdoc in Cerema. It's in one. In this team, they are interested in how to evaluate with a non-destructive method the structure and the materials. So they wanted to make an imaging, an ERM for the ground or for special materials. So when I arrived there, they hope only a Python code to generate mesh and to run inversion with it. And they have a problem with mesh. So I tell them, I know FreeFem, I can play with FreeFem and give you what you cannot do with your code. So this is the code Pilgrim. It was called Pilgrim. I add FreeFem FF for their code. And there is an interface graphic that it will be distributed also for other, well, it will be open. So here we have the cliff of Sainte-Marguerite-sur-Mer. It's in Normandy. They have a drone to take photo, and from the photo we use metashape in order to generate the point, XYZ point. And from this, we use Open 3D and other software, and at the end FreeFem in order to build the mesh. And here there are in the yellow there are the electrodes that they plant, and they send some electric wave, and try to measure the potential on with each measurement. So what I've done with FreeFem is to adapt the mesh around the electrode position here in 3D, following the distance to each one. This is the result obtained with their code, but it is mispatterned. But I use FreeFem in order to interpolate the solution on the old surface that I built with FreeFem. And as a result for their simulation, so here in this zone we have salt water, in this zone a dry zone, here a transition zone, what they call the bison salé. Here another application that I've done also for them, using the function disk of FreeFem. They have a model or a mesh in 2016. They have a new mesh in 2023, and they wanted to see the comparison for the erosion. And so using only this line with FreeFem, it gives this result. This is another mesh, PDF. It was hard to do it, but now it's done. And thank you for attention. And I can show you now how I built So here I take, so I build a sphere, okay, and I build a cube. For now, everything is okay for me. For the cube, I extract the border of the down and the border of up. So here, using extract, you can choose which label you wanted to. So this is the first photo, as you can see here. So there is no intersection between them. Okay, so I have a sphere, and what I'm showing here is just all the surface. So using sine distance from the mesh of KH2, which is only the plane, and I compute the distance on the sphere. So here you have here all this function, okay, and here you have the isosurface. So the distance is when the ds is 0. Okay, so this is the intersection between them. Then the TH1 here that I obtained, so as you can see, I already have this line. Okay, so I have two regions. I can just extract the line, which is the intersection between this THL is the intersection between the is a circle, just a circle. So after I can add this line is to extract the border of the square. Then using build mesh S, I can build the mesh. I can build the mesh of this region, so the outside. It's the square and the one. And after building this, this mesh, I will have two mesh, one inside, one outside. I can track the trunk region that I want. I can do a mesh adaptation if I want, just for the surface. And at the end, I can build the domain. With I obtain this mesh, which is cut it and I finish my presentation.
We have time for a short question. Otherwise, we never eat.
On the last figure, there are some isolated points where there are a lot of triangles with rather bad shape.
Yeah.
Yeah. Is it MMGS or is it?
No, because the mesh that originally built.
Yes, I saw it was right there.
Yeah.
So it's just from the beginning.
Yeah, it's from the beginning.
And so the beginning is with that mesh MMGS. Or is
No, it was
mesh.
no. It's the way that Guillaume Vergès and Frédéric Echt built the sphere.
Okay.
Okay. So there is a method that they use this method to build the sphere, and these points are distinct from.
Yes, sphere 20, it's the best way to have the most regular mesh on a sphere. Because you take l'isocaédron and you put the isocaédron on the sphere. And so the isocaédron is the most complex polyhedra, regular polyhedra. So direct to the sphere. And so here you see the 20 triangle of the isocaédron. And thanks to
Guillaume Vergès.
Guillaume Vergès, a student from Rouen. Okay, remark, your method works only because one surface are a plane. If it's not a plane, because you rebuild the mesh, it doesn't work.
You can give me something that it does not work, and I will. I have another technique also for this, but I didn't.
But it's clearly a good idea. And some time ago, somebody asked me to have the problem of find if two lines are too close or not with distance. You can know if they touch or not. With the sign distance, I'm quite sure you can solve your problem.
Supposing that both of them are intersecting, for example.
The time distance will be 0 in some part, and so you know.
Yes, but
so we can speak after or during the lunch.
Okay.
But I'm quite sure with that you can.
I've got another question.
Yeah.
Do you know if it's possible to extract a border type from a mesh type?
The border type of mesh L.
Mesh type.
The border of mesh L is point.
No, you want a border.
Yes.
Border is analytical, so you cannot.
Yes.
So no, you cannot. Once you have discretized your border, you cannot go back to something.
But when you
you can define a function which takes the.
I define like this.
Yes, we have tools to do that.
I already did this. I can show you.
Yeah, I did, but I wanted to know if there is a function, a special function.
It extract and then you order all the points inside border.
So I think this question is good in community. To have a true example and to.
So for the 3D mesh, you may ask me, I can. I'm now
We can try if you want this afternoon.
ready much.
But the problem is not really basic.